I'm going to speak in English. Hopefully most of you can understand. I'm Aasma. I'm here from Cybertec, as it's plastered in big letters all over the slides. We are doing Postgres support, performance work, and HA solutions, and basically everything related to Postgres. And I've been working with Cybertec for 7.5 years now. And I'm a contributor to Patroni, which has been talked about over here, but that's not what I'm talking about today. And I also have gotten a few patches in Postgres for, so that's a bit about me.
Sorry, it would be easier to hear you if you will speak directly to the
sorry.
microphone. Yeah.
Thank you. And my previous life had a decade in software development in the government sector, so I'm not a sysop guy by tradition, just something I happen to fall into. And if anybody has any questions after the slides and does not dare to ask me in person, you can email me at the email shown here. Forward. So what are we going to talk about today? I'm going to first start on what is a highly available system, so some definitions, so we're all talking about the same thing. Then I'm going to go over how to build one with Postgres, and then some best practices. And if you have any questions, feel free to interrupt me at any time. Alright, what is high availability? So availability is a trade-off. If your software is not working, it will cost you sometimes money, or maybe a reputation if your site is down, or maybe sometimes even lives. But adding availability also costs money and time and complexity. So you need to find a balance between how available your system is and how much you're spending on making it so. And if you need to find a balance, you need some way to measure it. So for measuring, one typical way is the number of nines, which is really not a good metric to measure availability. So usually it's like we have 3 nines of uptime, but is that good? So if you have 8 hours of time a year, which the math works out to, is it okay to have 8 hours of downtime? That's probably not what somebody means by highly available. Or if you have 8 1-hour outages. So it's not that useful for finding the balance. So a better way to measure availability is to first define what availability means, or what available means. So if your system can complete user interactions within 5 seconds, and 99% of cases it's under 1 second, you consider yourself available. Or you can define different kinds of numbers, but you should probably have some goals. How quickly should your system be able to respond for users to consider it available? And you may have also some definition of what is up but degraded. So system is working but is slow. And the second thing to measure is you want to target the maximum downtime for different classes of problems you might find with your system. And this type of measurement is still not great because it's really hard to figure out how often a problem can occur, or even what types of problems can occur. So, for example, taking the US space shuttle program, the NASA estimates for the first flights were that the failure probability is 1 in 100,000. But after the Challenger disaster, they did an internal review of how they calculated their risk estimates. And the reality was then that for the first flights of the space shuttle, the risk was more like 1 in 10, which is really, really different. But even the best people cannot estimate well what the probability of failure is. But at least trying is better than nothing. So for example, some types of risks or problems or things that could happen are regular, so it happens once a month or even more often. And like minor version upgrades. Hopefully everybody here is upgrading their Postgres versions, getting the security fixes and bug fixes. You also will have schema changes if your application version is being updated. And you will do configuration changes, adding servers, changing your memory settings, whatever. For these types of things, you actually need to have a system in place so that they are routine and they are not something that cause downtime in the sense. You don't want to worry about the things that happen regularly. This will give you some time to think about the stuff that is actually important and dangerous. So more of the things that can happen like once a year or thereabouts. And for those cases, you may find it acceptable that your service is slightly degraded. For example, if your server goes up in flames, then you can accept different levels of degradation depending on what is your response to the fact that the server is not there anymore. So if you order a new one, it will not arrive in 1 month. So 1 month downtime, probably not okay for most systems. But another option is to move the disks to a spare server. That will take a day or so for somebody to actually complete the task. Or if you are using a storage area network, you might have the storage guy come in and attach the disks to a different host and boot up the new VM. Or maybe you have a hot standby system and somebody triggers a failover. Or you might even have an automated cluster manager that detects the failure and automatically promotes hot standby. And this is like a spectrum of different responses that you could have to this problem. And depending on what kind of degradation you can accept, you may accept something that is not maybe perfect, but is good enough. So if it's fine if you're once a year your service is down for 1 hour, you maybe not even don't need to bother with the hot standby system. Then there are things that happen less often. Like somebody accidentally drops your database. And for these types of things, you might want to have a plan, at least for some of those. So if somebody drops your database accidentally, you don't want to just shut the company down and escape to some tropical island. You want to restore it from a backup. Or like a data center has a fire in it. Do you want to stay available, or can you accept that you're down for a day? Or in a more modern world, AWS is down and your service is down. Maybe it's fine. Half of the internet is down anyway, so you don't care. And if data center is hit by an asteroid or there is a thermonuclear war, well, there is no civilization, so nobody needs your service anyway. So no point in trying to fix that one. But for something like fiber optic links cut by picking equipment, you maybe want to have a second offsite that you can boot up at short notice. All right, how to build one? So the main point is if you only have one copy of your data and the system that is storing this one copy breaks, you lose availability. Simple as that. So first thing you need is some way to have multiple copies of your data. That is replication. And if you have multiple copies, it's like the man with two watches. He never knows what time it is because they might be showing different time. So you might need to agree on which copy of the data is correct. And there are multiple ways to do it. In PostgreSQL, it's usually done by always having a single master. And you also need a failure-tolerant system to decide which copy gets to be the master. And failure-tolerant here means that it has to work when everything is going wrong. So some server is on fire, somebody cut the network cables, and the 10-year failover system needs to work. So that's the difference between normal systems you build and failover systems. Failover systems need to actually work under the worst circumstances. They expect everything to be broken, and you want their systems to still act reasonably. And finally, your users will need to find the system that is currently the master. So you need some kind of connection routing to make the users go to the correct server. So let's see this as a picture. Here we go. So we have an application that has some requests coming in. There is a connection routing system somewhere here that will direct the request to the correct database system that will replicate it to a secondary system. To that, have some cluster controllers that will manage everything to pick which database is the current master, which one is the standby, and then you need to have some consensus for the cluster controllers so they agree who is currently inside the cluster, who is outside, is the network broken or is the other one down, what is going on. And some additional pieces that the highly available system has to support its operations is backups, because this system can still break, for example, the drop database case. It will be happily replicated as a user request, and you will need to have a backup to restore it from. Or a different case that a hacker breaks in, encrypts all your data, asks for ransom. It's, again, helpful to have a off-site backup available. And then also monitoring. If your database is slow, then you still might not be considered available. And no amount of failover is going to make your database fast. It's only going to make it slow. You need to proactively monitor for slowness. And of course, operating procedures. Every high available system is only as good as the people operating it. I have seen more operator errors than servers failing, so having good procedures is a must. Now a brief tangential about multi-master. A lot of the time people who come to me asking what high availability say, what is the multi-master solution for Postgres? And what they don't understand is multi-master is a different thing from high availability. You can use multi-master to provide high availability, but it is not the same thing. And it's a slightly larger topic that I will not cover in this talk, but I will point you to this really, really good talk by Craig Ringer from Second Quadrant, who wrote a Postgres multi-master system called PDR. And he will convince you why you probably don't need multi-master to do high availability. The short reason behind it is the speed of light. There is, if you know CAP theorem, then there is an expansion on the CAP theorem that says that if your network breaks, then you have two options. You either have to choose to be available or consistent. And if your network is not broken, then you have to choose between being fast or consistent. And in Postgres world, the users are usually expecting the system to be consistent. So multi-master will will not provide that unless you can provide perfect network connectivity. All right, jumping on to replication. The different ways you can replicate Postgres are, for one, storage-based, which is the old way how people used to do it. So we would have something like a storage area network, which is a really expensive high-end box that has smarts built into it that will replicate all your data between one box and the second really expensive box. And the vendor says that it will definitely never break if you trust him, which I do not recommend because they do break occasionally. But you can also build a similar thing using open source tools. For example, DRBD is a way to do block-based replication. When Postgres writes something to this, it gets replicated synchronously. And the problem with this type of solution is it has much longer failover times because when you need to fail over, the secondary system has to perform crash recovery. And then high write throughput systems, this can take upwards of 5 minutes or more. And the bigger problem is that you have to be really, really careful to not corrupt your data. So if you break something in the storage area network-based system and you accidentally attach the same disk to two working databases at the same time, then they will go in and corrupt the data. Then you have 0 working databases after it. Whereas with higher level replication solutions, if you accidentally have a split brain, you will end up with 2 different copies, but at least both are working. Still not great, but better than having 0 copies. The next option is replicating transaction logs, also known as streaming replication, which is the standard way how you do replication in Postgres. So if somebody says Postgres replication and doesn't specify anything more, they usually mean streaming replication. And if you want high availability, you probably want to use this one. Most importantly, because it's pretty bulletproof for data consistency. It's hard to break the streaming replication in a way that corrupts your data. You might break it in a way that your copy falls behind, for example, which you would have to monitor, but you don't have silent data corruption, like with some other replication solutions. And finally, there's logical replication. When transaction log replication is replicating, it replicates changes to the disk. It replicates that on this page on the disk, add these bytes on this location. But with logical replication, the replication is specifying on the row identified by this value, update this field to that value. And the difference is with transaction log replication, you have much more data to replicate because you are replicating not only the changes you are making, but you are also replicating all of the index updates and maintenance work that the database is doing. But with logical replication, you are only replicating the data and you're much less dependent on which version you are running. You have less network throughput and so on. So it's kind of nice, but unfortunately at current state, there is no high availability solution available for logical replication. So if you want to use this, you get to build your own solution. And with the current state of Postgres, your application also needs to be coded to work with logical replication. Because, for example, schema updates are not replicated with the replication that is built into Postgres since version 10. But in some use cases, there is no other solution. So if you need to replicate, for example, 10 tiny databases to a single big one in the center somewhere, then transaction log replication does not work, but logical replication can bail you out. So sometimes we have no option. Then on to cluster management, which task is to then figure out who is master and then make it happen. And the main thing about the cluster management system is that if it's a correct solution, you will have at least 3 independent nodes in your cluster. Not all of them have to have a copy of the database, but you need 3 nodes to agree on who is currently connected, to whom, and who is down. So if the master has its network broken, how does it understand that it should remote itself if there is only a second copy? There is no way to figure it out. So fundamentally, any solution that says that it works with 2 nodes is broken. And what kind of features would you want in a cluster manager? So one is the consensus-driven failover. There are algorithms like Paxos and Raft that can work under really bad network connections and always come out to a correct answer, so that the majority decides who is the master, and there is always one node that gets to be master. And basically, I have not seen any other way to do it that is correct. All other approaches have some ways to break it in a way that you will have multiple masters and potentially broken data that you will have to merge manually. Another feature to look for in a cluster manager is the capability to manually switch over. Some of the tools do not support this, and it's a real pain when you have to do maintenance, because you need to do like basically trigger a failover, which is much more downtime than a graceful switchover. Then again, for maintenance, sometimes you do not understand what is going on. You need to dig in and put the system back up manually, and you want a way to tell the cluster manager, get out of my way, I need to get the database back up quick. And do not interfere and do not undo my work. So that's what's called a maintenance mode in those cluster systems. Then synchronous replication support is nice. Mostly people, when they store data in a database, they expect to get it back. And actually, I think synchronous replication should be the default, and having it off should be an optimization that you do when you can say, okay, I can lose a few transactions now and then it doesn't matter. For example, if you are collecting metrics, it's not a big deal if you have a hole in your graph, but it is a really big deal if you lose an order or a payment information or something like that. Helpful thing to have is automated cluster rejoin. So if you have 2 copies of your database and one crashes, you don't want to be paged immediately to come into the office and bring it back up. If it can automatically rejoin the cluster, you get back your insurance policy much quicker, and this reduces the window of risk by a lot. Especially if you have rolling failures. So one system fails, then another one fails, which is pretty common in cloud environments, and especially in containerized environments. Then automated node provisioning. If you need to add a node to the cluster, it's really, really nice if it's just a plug and play. Just throw another one in there and it figures everything out. And the backup system integration. If you have a terabyte database and you throw a new node in it, then it needs to get a base copy for itself from somewhere. And if it pulls it down from the master, then the 1 gigabit network interface, for example, will die under the load. And your user experience will be highly degraded. So if the new replica can pull its copy from a backup system, then rejoin the cluster, that's a nice thing to have. And finally, Watchdog or Stonit, we heard new stuff, but Stonit is shoot the other node in the head. So when a failover happens, we want to make sure that the other node is dead. And sometimes the cluster manager has bugs, for example, or the hardware is just freezing up for a few minutes at a time, or something like that happens. And then you need to have a way to make sure that when the other node comes back alive from the zombie state, that it doesn't present itself as a master that accepts transactions but potentially loses them. And for that one, there is a watchdog option where the watchdog is basically the system itself having a really low level iteration going on that says, is everything fine? And if it does not get poked frequently enough, if there is not a heartbeat, then it will just reboot the system and trigger a normal failure. Whereas Stonit is slightly similar, but in that case it's the other node triggering some way to kill the other system. For example, by connecting to the server power management board and telling it to power cycle the server. In my experience, the watchdog-based approaches are much more nice because they are more compatible, and the Stonit has really bad failure cases where if you make a configuration mistake, you can have a system where everybody is coming up and shooting everybody else, and you have when the server, every time the server comes up, it has like 5 seconds to be awake until another one comes up and kills it. So you will have to, in the 5 seconds, log in and disable the configuration to bring the system back up, and that's not a nice problem to have in production. So Stonit has pretty uncomfortable failure modes. And now for the cluster manager that you might use for Postgres. My favorite is of course Aasma, which solves the really complicated consensus problem by not solving it by delegating it to another system. Basically, outsources the consensus problem to etcd and only solves the problem of managing Postgres. And it has basically all of the features on the previous slide available. It's fully automated and suitable for both bare metal hardware and also in a cloud environment where you are running Postgres inside containers and might be maybe using Kubernetes to manage it. But its downside is that it's more of a tool than a solution. So you would have to, Aasma solves the cluster manager problem, but for the other problems that we talked about, other pieces, you would need some other solutions to put the whole code together. Whereas the next one, Stolan, it doesn't have as much features on the bottom of the list, but the basic architecture is the same. It uses external consensus to figure out who gets to be master, and it has a built-in proxy system that handles the connection routing. So that one is slightly easier to set up due to that. Then you might have run into a rep manager. This one does not use a consensus system, it uses some ad hoc system with a witness server, which I'm pretty sure is not correct, but I'm bothered to figure out the exact failure case for it. But it's might be simpler to set up, and it's more oriented towards manual operation and rather than automatic failure. So if you want a simple tool, you might find it nice. Then there's path, which was, what was it, Postgres availability framework. I don't remember what it stands for, but it's basically a pacemaker and crossing-based resource agent that uses pacemaker to solve the consensus. And if anybody has used pacemaker, they will know how complicated the system it is. So if you do not know pacemaker, do not use path. If you know pacemaker, then you might consider it. But you also might consider moving off of pacemaker because it's a nightmare to debug. And we have a new entry from Citus for PG auto failover. That one also has an ad hoc system for determining who gets to be master and who gets to be standby. It only supports 3 node clusters with 2 copies of data and then 1 manager node. And looking through their state machines, it seems like PG auto failover has similar problems to Rep Manager in that it does not handle all of the network failure cases correctly. It makes some assumptions about what your network looks like and what kind of failure modes are possible. And if the failures do not happen like that, then having a split train where you have multiple masters and losing transactions due to that is possible. And finally, PG Pool 2 also has a way to promote systems, but that's something that I do not recommend. It's pretty hard to set it up in a way that is actually reliable. Alright, now on to connection routing. So this is the part that takes the master chosen by the cluster manager and makes sure the application gets to the correct master. One way to solve this problem is to have a floating IP for the master server. So one of your nodes has one IP, second one has a second IP, and then you define a third one that gets assigned to the node that is currently master. And this is moved around by some tool. In Patroni, there's Patroni world, there's VIP manager available. Within Pacemaker world, with PAT, there are IP address tools available. But the main thing to consider is that if you do a secondary IP address, which will then do an ARP broadcast for the network-oriented player, this will mean that your databases have to be in the same subnet. And if you have multiple data centers, then having everything in the same subnet might not be possible, depending on the network vendor. And another way to have a floating service IP is software-defined networking. For example, Kubernetes will have a software-defined networking layer that has some magic with IP tables to make sure that on every server, if you connect to the service IP, it gets routed to the node that is currently master. Next way to do it is to have a DNS record. So you have a name, master service, whatever, and your DNS server will have a record pointing to the master. And if you do a failover, then you just change the DNS record. With older DNS servers, that's hard, but usually this is done using something like console, which will have service availability checks and will then respond with the correct IP address for this master service. The problem with the DNS record is that some client applications helpfully cache the DNS response, for example, for 1 hour at a time. And you might discover this when you do a failover, that some of your clients that are connecting to the database are connecting to the wrong database for 1 hour, and then switching over. So that's the downside of using the DNS approach. But if you can avoid those clients, avoid having such clients, then the DNS-based approach is reasonably good. Next one is to have a load balancer layer. or another way to put it is a proxy layer. So it's basically a separate service that accepts connections and then routes them to the current master using some health checks, for example. And you can put this load balancer on the database nodes, for example, which is what Stolen does. So in that case, let's go back to the diagram that we had here. So in that case, on each database node, you would have a proxy, and if the application connects to the one that is standby, then it just routes back to the master. Another place to have the HA proxies on the application side. So on each application server, you will have an HA proxy server, and the application connects to the database in localhost, and the HA proxy figures out where the master is. And the third option is to have a separate layer for the connection routing. So you'll have a HA proxy server, or probably multiple HA proxy servers, because HA proxy itself also needs to be highly available. And then the proxy server will, the application connects to the proxy layer, and the proxy layer routes to the database layer. Bonus points for this type of solution is that the proxy layer can actually figure out when the connections, old connections need to be terminated. So if you have trouble with timeouts being too long, it can help somewhat. It can fix troubles in other parts of the systems by having a load balancer layer that just terminates TCP connections that are stale. But the downside is you have more pieces you need to install. And if it's a separate layer, more servers. So main recommendation is if you have a load balancer available, consider using it, but if not, look at other options first. And finally, for the other options, it's client library for application connection pool logic. So in JDBC or Postgres clients that are using Replication version 10 and above, you can specify that the hosts in my database cluster are node 1, node 2, node 3, and connect to the current master. And then with JDBC, it will try each node and then remember which one was master. And next time somebody connects, it will connect directly to the master node. And if it's not master anymore, it will redo the discovery process. On LeapPQ, which is the Postgres client library used by stuff like Python and anything based on C, it will have the same type of solution where you can specify multiple hosts, but then each connection attempt is to redo the discovery. So you have to take a really close look at your connection timeouts and when you are doing your connections. So if every request to your system is doing the discovery process, and the discovery takes like 5 seconds due to timeouts, you might have trouble. But as it's not really hard to have a connection pool logic to just figure out which database is currently master, you can query the cluster manager, who is the master, and then make sure that your connections are to the correct host. It's reasonably easy to just modify the application to discover it on its own. And disaster recovery, backups are really, really important to make sure you have availability, especially for the rare cases. So your cluster manager will cover the stuff that happens regularly. Your network breaks, your servers break, Postgres crashes, whatever. Linux kernel has a bug. That will be mostly taken care of by the cluster manager. But sometimes there are stuff like the cluster manager itself has a bug, or somebody deletes all your data, or whatever happens, for those cases, you want to have a disaster recovery plan with the backup. And you have to specify what is your recovery time objective. So when the worst happens and you have to recover from a backup, how long can you afford to be down? And you need to take this into account when designing your backup system. So if you have a multiple terabyte database and only 1 gigabit links, then you are not going to restore it in 1 hour. And similarly, there's a recovery point objective, which is saying when there is a disaster, how much data can we get back? What is the freshness of the data? So is it since the last backup, which might be 1 day old, or is it 1 hour or 5 minutes? How much data can we afford to lose in a case of disaster? And for the recovery point objective, if the latest backup is not an acceptable solution, you need a transaction log archive or WAL archive, and then you need to do point-in-time recovery processes on top of this. And if you cannot lose any transaction at all, then you could build a system using, for example, Postgres receive wall, which is like a replication client for Postgres that just receives transaction logs like a Postgres replica. And then set up synchronous replication that makes sure that the backup also has a copy of every transaction that commits. And this will give you 0 recovery point objective, which means every transaction is always backed up to the backup system. And you would also want to set your backup system up so that you cannot accidentally delete your backups or overwrite them with bad data. Any questions so far? Before we move on to best practices.
No, let's continue.
So you mentioned the tools. What's the price for these tools?
Everything I have talked about here currently is open source.
Open source.
Yes.
So
If you want somebody to hold your hand setting them up, then that's all, of course, extra. But all the tools, where is this slide? These tools are all open source, with mostly pretty permissive licenses. BDR, I think, is like half open source. Not sure about that one. I'm not even aware of any decent closed source cluster managers for Postgres. Yeah, you would have closed source cluster managers if you buy database as a service from, for example, Amazon or Microsoft or Google. They will have a closed source thing, but in that case you are paying it for the service. But everything we are talking about here is open source, and for example, Patroni is basically good enough for everything you will need, in my opinion. And if it's not, contact me and make sure it is good enough. So, best practices and timeouts. If the server goes up in flames, then it's not nice enough to tell your clients while waiting on a query that, okay, shit, I died, no response coming. It will just silently fade and everybody will keep waiting. So you need to have timeouts. Timeouts in place to detect failures. One of them is connect timeout. So when somebody is trying to connect to the dead master, you want them to figure out sooner than the default that the server is down. I think the default is like 30 seconds or 2 minutes or something like that. And that might not be good enough. So set the connect timeout that is suitable for your expected failover times. Similarly, if somebody sent a query to the server and is now waiting for the server to respond, then if it dies, then there is no communication going on, and it will just keep on waiting until there is a TCP mechanism to close idle connections that are dead, which is controlled by keep alive idle interval and count parameters, which are available both on the server side and on the client side. And in this case, you want the client side options to specify that, okay, if the connection goes idle for 1 minute, just send a packet asking, are you still alive? And it will send the count number of packets with the interval, within interval seconds to see, and if every one of those packets goes without an answer, then the connection will be dropped and then you can reconnect and retry. DNS caching timeouts, as mentioned, if your DNS is cached for 1 hour, then you will not fail over for 1 hour. And the load balancer settings also matter. So load balancer has times, health check times, when it, how often it checks which one is master and which one is not. And it also has one markdown shutdown sessions, which will mean that if the load balancer discovers that the old master is dead, it will tell all of the clients that the connection is now terminated because the other node is not happy. This one markdown shutdown sessions is HA proxy for Nginx or F5 TYP or something else where you will need to look at other parameters. That basically means that connections to the dead server will be terminated actively. Then what to do when the timeout expires? You want to have some kind of traceable error handling. So one way to have a retry loop is have the user sit on the computer, get a sad face on it, and then hit F5, see it refreshes it. That's one way to do a retry loop. But you can also have some kind of a retry loop within the application. So if you have switchovers or slight hiccups in the system, for example, with Bartoni, your switchover will usually take around 1 second. So you want just the application to, if it gets an error back, just retry it once and see if it now works. And then users will not even notice that you did a failover. But having the retry be like 1 hour long does not make sense because the user will just walk away after 30 seconds anyway. So have some error handling, but have a timeout on that before you give a sad face to the user. Then it's really important to understand what are your actual durability requirements, because durability and availability have some conflict between them. If you do not need, if anything the user sends does not need to come back, you can always be available. It's really easy to be available if you are not storing anything. But on the other hand, if you always need to keep data, then it's, if there is any chance to lose any data, you have to become not available. So these two requirements are in conflict. But it's not like only durability and only availability. There is a gray in between them. So in some cases it's fine if you lose some data now and then. It's okay, it's only logs or only metrics. It does not matter if something is lost. And in other cases it's okay, fine if you lose some data. Maybe the user can, maybe you are storing some settings and users just can re-enter their settings. Or if if you get notified by it, then maybe there's a paper copy and people can just re-enter the data from the last 5 minutes before the failure. But sometimes you always need to have 2 copies of the data. So if one server blows up, you definitely have a second copy of your transactions. And sometimes it's important to have that there's a copy off-site somewhere where it cannot be deleted anymore. So you have a copy in your backup system, but it's not possible to use the normal network interface to delete it in case a hacker comes in and tries to delete your backups, for example. So there is a spectrum there. But normally when people are using a database, they actually want you to store the data, so you probably want the synchronous replication. And with normal Postgres synchronous replication, the accepted knowledge is you want to have 3 nodes, the synchronous replication and high availability at the same time. Because otherwise, if you have synchronous replication with 2 nodes and the standby goes down, then everybody will wait and your system will become unavailable. So that's why you would want to have 3 nodes. But with Patroni, there's also a mode where it can continue to function with 1 node, but then until it cannot fail over anymore. So if you have only 2 copies of your data, the standby fails, Patroni will reconfigure the master to work in an asynchronous mode. But if the master now fails and the standby comes back, it will not be promoted anymore because it doesn't have the latest data and it's not acceptable as a failover candidate. So it's a nice balance between having availability and not losing any data. So the Patroni synchronous replication mode or synchronous mode will ensure that you will lose 0 transactions due to automatic failovers, which is a good middle ground. And if you have applications where some of the data they are storing is important, some is less important. For example, logs are stored in the same database as financial data, then application can actually in Postgres relax durability requirements per transaction. So the application can set synchronous commit. 1 means okay, we want this transaction to be synchronous, but you can also set it off. Try to store this data if possible, but if you cannot, no big deal. And this is something that is pretty unique for Postgres. I haven't seen any other relational databases that has this kind of replication mode that can be synchronous for 1 transaction, but the next one can be asynchronous. It's really important to automate everything that you can and simplify. Make everything as simple as you can and as automatic as you can. Because every time you need to manually go in and to fix something, it's a chance to make a mistake. You are sometimes on a wrong server or enter a wrong command, have a copy-paste error or whatever. If you can automate it, you eliminate the potential source for mistakes. But then again, every automation is a chance to create bugs, so the automation can also be wrong. And for that, test, test, and test. This is actually the most important thing about high availability. If you do not regularly exercise your high availability system, it will fail you when you need it to work. And test as many scenarios as you can and verify that you actually understand how the system works in that case and why does it work that way. So when you run into trouble, you are not confused at 3 a.m. and something is not working. And everything is on fire and somebody is watching over the shoulder asking when is it fixed. So try pulling the plug, which means just shut down the server, kill the VM, whatever. But also also try network failures, and not just cutting the network to one server, but try partial network failures when somebody sets up a firewall wrong. IP tables is a good tool to simulate network failures. See what happens when the disk is full. See what happens when you run out of memory. See what happens when you hit the database system with much more transactions than it can handle. See what happens if you do multiple failovers in a row quickly. See if you can actually recover the system from a backup. And exercise how recovery from those scenarios needs to happen. So when the shit hits the fan, you know what to do. And use battle-hardened tools. So people have run into all kinds of crazy problems with some of those cluster management tools. And they have learned from them, made fixes to the system, and now they are working better. And if you're trying to build your own system, you will get to discover all of the same problems on your own. So if you can, use existing tools. For example, Patroni found out that Postgres will not start after the server reboots. If the postmaster page has a PID number that happens to conflict with a process that is not Postgres or the process that is starting it, but is running as the same user as Postgres. And this happens like 1 time in 200 restarts. Because the operating system hands out PID or process ID values somewhat deterministically, so starting as a counter. So it's kind of common to have similar PID numbers. And for this, Patroni has a check for it, that it checks actually that the PID number, so if the postmaster PID points to a process, that the start time is actually correct for it. And monitoring. If you have to monitor one thing, monitor that your replication is working. Because if your database is down, your users will tell you. But if your replication is not working, you will just discover when you lost data. So if you have to monitor one thing, monitor replication lag. But you do not have to monitor only one thing. Monitor also that the database is working at a reasonable level of activity, that it's not overloaded, but also that it's not completely idle, because that will tell you that there is a problem somewhere else in the system. Monitor that you have enough disk space, because running out of disk is a pretty common problem, and it's really annoying to recover from. Monitor that your logging is fine. So, for example, if you have a long-running query, somebody runs a report that runs for 2 hours, and then you want to do an alter table somewhere, and everybody will block on that alter table, and your database will be down for 2 hours behind that log, unless somebody goes in and fixes it. So monitor logs, and also monitor query performance. Check out if, for example, auto-explain, and use auto-explain to log slow queries and try to fix them. Because if the database is not responding quickly enough, that's also an availability problem. Not only that it's not only enough that the database is up, it also has to be working quickly enough to fulfill its purpose. So, in summary, what you need to remember, if you need automatic failover, go for something robust, because automatic failover that is not working properly will create more problems than it will solve for you. So use a good tool and use an existing tool unless you have a very good reason to build your own and you are prepared to maintain it. And a high availability system that is not tested is much worse than not having a high availability system at all. So no HA system is at least simple. And that's it. Questions?
You mentioned that there is some custom approach to build a replication system. Have you ever seen such system was implemented by someone?
Yes, I have seen some logical replication systems that push data to central locations.
So written by individual customer, yeah? So individual company for its own purpose?
Yeah, not a generic tool, just a special case solution.
What was synchronizing? Was it synchronizing like only the data or all the database as a whole? Because what, for example, if they use right to synchronize the data, and problem will be on the physical structure, how they will recover from replica. If they synchronize only data, not like indexes or system objects.
So yes, the logical replication only synchronizes data, so they have procedures how they deploy schema changes that they can do incrementally across all servers. So you have to do it in a way that is backwards compatible among steps. So in the index, so you need to have processes in place that deploys it on all systems in the correct order. And unfortunately, not a magic silver bullet there.
Can you specify how will Patroni handle a brain space situation when we have an even a number of nodes, but when there is a situation when we have an odd number, so that we avoid brain space. But if some node is unavailable for some reasons, how will it be handled by the Patroni?
So let's see if I understood this correctly. So if some node becomes unavailable and then it comes back, can you explain the scenario again? So
the scenario is that does Patroni have an option to spin up an instance? The situation is that how we get to the consensus when we have an even number of nodes.
Okay. Let's go back to the architecture diagram. Here. So in Patroni, the cluster controllers are on this picture. This is Patroni that is running on the database nodes, and this consensus is outsourced from Patroni to etcd, and you would have to have quorum. So the consensus is on the etcd side. So we need to have all numbers of etcd nodes. There's no whiteboard here, but
yeah,
so.
I understand. But in real situations, we can have a situation when one of the nodes is down. For example, it can be if we have a cloud solution, it can be one availability zone that currently is unavailable, and we have only two nodes. So
Patroni will actively keep track of synchronous replica. If you set up synchronous mode on, it will check which nodes are available and keep track of where are the latest copies of the data. So if the one availability zone goes down, then it will be not considered as a failover candidate and until it comes back up, it is picked as a synchronous replica. And this information is stored in etcd in consensus. So.
Okay. It's okay.
Well, we can maybe discuss it
Yeah.
over beer or something.
Thanks.
Thank you for presentation. I have a question. We talked about trade-offs between availability and consistency. So, and you mentioned asynchronous queries, right? So you can, for example, application sometimes if they need high availability, they will use asynchronous transactions. And are there any maybe tools or methods you can advise to combine both high available and consistent system in one database, in one setup? Maybe some tricks, maybe some tools.
Well, in Postgres, if you are only using the master, it's always consistent. So even with asynchronous transactions. And if you are trying to query the standby, it's always inconsistent unless you are doing synchronous commit equals remote apply. But there is another great solution right now. People are working on it that have like proper read offload with serializable semantics. So
With what, sorry?
So if you want to have read offload to standby servers and would like to have like a consistent picture that if you write to the master and then you read from the standby that you are actually seeing the data that you just wrote to it. This one Postgres does not have. Well, remote apply is an accurate way to do it, but that currently isn't a good solution for it. But there are some work is being done on it, so maybe Postgres 13 or.
Okay, so it's not. Okay, thanks.
So keep track. If you want to keep track of the patch, it's called, I think, causal reads. What's the patch name?